Just basic thing which I wanted to talk about is first about an introduction to dislocations a little bit, but most of the introduction has been covered. Okay, just why we require dislocations, and then about dislocation characterization, because all the theory which we talk about, finally we have to observe the dislocations in the sample, correct? How to observe and characterize the dislocations, what all parameters which we have to characterize, that is what I will try to cover. The rest of the lectures will talk about the various types of defects which are going to be there, with which these dislocations will interact, and all of them lead to plasticity. That is also another aspect which will be covered. Okay. Now I'll just ask a question. In metallic materials, we wanted dislocations. Can you give situations where we don't want any dislocations? We always say that if dislocation is not there, that material is good. Which material? Not turbine blades. Electronic materials. All electronic materials, if dislocation is going to be there, the performance of the material will be poor. There we would like to see to it that dislocations are removed from the material. Whereas for a material to give a good performance, structural materials, we need dislocations. In both the cases, we have to study dislocations to understand, so that we can find ways and means how they give rise to strength in one case and how we remove it and try to get better properties, electronic properties. Okay. And we know that if we take any material and just try to apply a shape deformation, the moment of the dislocation which is important for shape deformation, that's right. And that we can calculate it, that strain we can calculate it by just vector times the dislocation density, okay, times the average distance the dislocation moves, correct? If this sort of a deformation, we give it on a single slip plane, okay, single slip system activates, and this much of shape strain is introduced in the sample. What will you see in the material if I observe that sample in the microscope? Will we see dislocations? Any take? I take a sample corresponding to the shape strain, and all the dislocations are moving in one single slip plane. What will we see? Okay. The sample will get deformed, correct? This is the shape which we use. We just have deformed it to this shape. But what will be remaining within the material? Will there be a dislocation? Yeah. Since it has moved, within the sample you will not see any dislocation if a single slip system activates. Okay. But these are all the type of dislocations at intermediate stage you see. But unless all of them come out of the sample surface, the shape strain will not be there. Once they have moved out, what is there within that sample? Nothing. Right? This is how a deformation will take place if it's a single slip system. Now let us consider the case, the same deformation but on two slip systems. Like here you can see that a dislocation, one moving it like this, another moving it like this. If they also come out without any interaction, the net effect will be no dislocations will be seen within that sample, correct? But it can happen that dislocations can interact during the motion. When they interact, some of them will become sessile dislocations, some of them will go into forest dislocations, and these are all the dislocations which we are going to see in the material, right? So finally we will be left with the dislocations which have disappeared. Some dislocations are going to be the red ones which I had used to show that they have come out of some dislocation reactions, others are the original dislocations which are stuck there. So this is the sort of a microstructure which will come. These sort of dislocations generally in plasticity, crystal plasticity, they call it as statistically stored dislocations in the material, which you might have studied, okay? And that the dislocation density and the total dislocations which are required to cause the shape strain, we call it as geometrically necessary dislocations, correct? These terminologies you might have studied, okay? And the total dislocation density will be a sum of all these aspects, okay? If you take a polycrystalline material, then what's essentially going to happen is that we'll have a grains. There when the deformation is being given, the grain should not come apart, okay. So because of that, what's going to happen is that there are going to be constraints, but it has to deform uniformly. That will lead to a lot of dislocation interactions, and we'll be finally left with lot of statistically stored dislocations, then geometrically necessary dislocations. All these things are going to be present in the material, okay. And there are many cases which we can consider where, like a microstructure, if we take a torsion, there also plasticity gradient will be there, lot of dislocations will be introduced. Then if we look at bended sample, then also the strain gradient is going to be there. So for that, geometrically necessary dislocation has to be created. Here under indentation, you can say that the plastic zone which is created, there's a lot of dislocations are necessary. Similarly, if you take ahead of a crack tip, there's a plastic zone. There are many cases, hard particles are there. All these cases have been considered in the last few lectures by Professor Fivel. Okay. So here, since they are hard particles, some dislocations have to be generated around them, okay, to compensate that, to maintain the strain continuity, correct? So when grains also, the same thing which happens. So all these considerations, finally what happens is that in the material, now you are left with lots of dislocations which are geometrically necessary dislocations. Then some dislocations are glide dislocations which are moving. Some are statistically stored. Some reactions lead to some sessile dislocations, various types of reactions which can occur, which you have studied. Then some of these dislocations move and rearrange themselves into cell walls during deformation, some into sub-boundaries. Then some get absorbed into a grain boundary, and some networks they form. So these are all the various ways in which the dislocations are distributed within the material. And if we know the dislocation density, using these relations we can try to calculate what is going to be the stress which is associated with it. For each type of dislocation, there will be a particular strength which is associated with it. And then we can calculate the sum of it, different ways we can take it, either a linear or a quadratic way, and then we can find out what's going to be the total stress. This is what is being done in the plasticity. That means to relate the dislocation in the material to plasticity, okay, we should know what all the types of dislocations which are present, okay, and what is the dislocation density and their interaction. All this information is necessary. So this has to be, we should have a way to observe all these things in the material, correct? So in this slide, what I have done it is, generally if you take a single crystal, what all types of defects can be there other than dislocations? One, it could be point defects, vacancies, and interstitials could be there. Their agglomeration leads to vacancy clusters and interstitial clusters, which can form Frank loops, which Fivel has covered, okay? Then planar defects, if the stacking fault energy is low, we'll have stacking fault energy. Then volume defects like watts can be there, second phase precipitates can be there. All of them have a role to play in the hardness of, because anything which is other than the matrix phase, you can call them as a defect in the material, okay? When material is being deformed, the dislocations have to interact with all these defects. This itself can generate dislocations, and also this changes the mechanical behavior of the material, okay? But if you take a polycrystalline material, in addition to it, you have grain boundaries. There are lots of grain boundaries, there are low angle boundaries, there the classification tilt, twist boundaries, then special boundaries, twin boundaries are there. Then if it's ordered phases, there are some interface between these boundaries. So all of them act as obstacles to dislocation motion. So that is going to change the hardening behavior of the material, okay? Then even orientation between different grains can alter the mechanical properties of the material. So that means that understanding dislocation or characterizing the dislocation is very important, okay? So the first thing which we have to understand, what are the parameters which we have to characterize to say that we have fully characterized the dislocation? They are: one, what is the Burgess vector of the dislocation, and what is its magnitude? because we know that when you calculate the energy corresponding to a dislocation, it depends upon the Burgess vector, correct? Then in that equation also which we have written relating stress to the dislocation density, the Burgess vector comes into the picture. So its magnitude is very important. Then what is the line direction in which the what is the line direction of the dislocation? What is the plane on which the dislocation is lying? These are all the important, these three information if we have, then we know that we have characterized the dislocation completely, okay? That's what crystallographic information, all of them. If you know the crystal structure, then in which direction which is going to be there, what is the Burgess vector direction, what is the line vector direction, what is the slip vector or the vector normal to a slip plane, all this information. Then we would like to know, on that basis, if that information we have obtained, we can talk about whether the dislocation is a screw dislocation. This information, if it is available, we know that if the line direction and the Burgess vector are perpendicular, we know it's a screw dislocation. On this basis, once we have characterized, we can talk about whether they are screw, mixed or edge dislocation, or shear or frank loops. All this information about the dislocation we can obtain, correct? So these are all the information which are required, which we have to get it from an instrument, correct? And then another is whether the dislocations are straight, kinked or jogged, all these aspects, okay? Then most important thing other than that is the number density, which is also required when we wanted to find out what is the stress which it, internal stress which it generates, correct? So this much information is necessary about dislocation, and this is what we have to obtain from a microscope, okay? For which what we do is we use transmission electron microscopy, okay? Microscopy is where we try to magnify the image, okay, and look at it, okay. And this is done using a lens system, correct? Right? You can talk of microscopes without lenses. Any microscope which is there without lenses? Not there? Sure? What is atom force microscopy? No lenses, right? You have scanning tunneling microscopy? No lenses, okay? There are systems are there which can do it, okay? But microscopes which we use have generally the optical microscope or transmission electron microscope, we use as lenses, okay? So the information which we can get in all these microscopes are crystallographic information and image information. What is crystallographic information? What do you mean by that? It's essentially about what directions and all, crystallographic planes, those indices, we can get that information, correct? How can we get this information? This information can be obtained from the diffraction phenomena which is occurring in the material, correct? And then image information is nothing but magnified image of the object which we are getting in. Okay. Now the question is, what is diffraction? Okay. Diffraction is nothing but from a sample, like for example, if we take a sample like this, from every point on the sample surface, okay, if a probe of radiation is falling onto it, it gets scattered in all the directions, right? So if I look at the probe, which is the radiation which is scattered in a particular direction from various points of that sample, when they join together, suppose we can make some lenses to make them join together, or they join together at infinity. And what is the total amplitude, provided the probe is a coherent one? Then we say that constructive interference is when they all add together. That's what a diffraction is about. So diffraction is nothing but rays scattered from different points on the sample, but in the same direction. What is the net amplitude which they have? That's what diffraction is. What is image? Image is nothing but the rays which are scattered from one particular point in all the directions. When they are brought together into an image plane, joined together, That is what an image is. So this understanding you should have. What is diffraction and what is image? Okay. What does a lens do? Okay. This is just I had mentioned about what all the types of interactions the beam can have with the sample. Okay. In this, the electrons are elastically scattered, the transmitted, and inelastically scattered. Elastically scattered electrons are the ones which are used for image formation and diffraction. Inelastically scattered electrons are the ones which we use to get spectroscopic information about the composition of the material and all these aspects, correct? So in a lens, if you look at it, you assume that the beam of radiation is coming from here, okay? And then the rays which are scattered, we know that for a lens, which are all parallel to the optic axis, they are all focused to a point at the back focal plane. So rays which are slightly away from the optic axis, but they are parallel to each other, they will also be focused. So at the back focal plane, what we get is the diffraction information in a lens. And the rays which are scattered from different points in the sample, they are all brought to a focus at the image plane. That means that the property of any lens is that we can get diffraction information as well as the image information from the same sample. It's an inherent property of a lens. You understand that? This is what you have to remember first. That means that from the same region of the sample when the beam passes through, using a lens, you can get the diffraction information also and that image also. So this is one which is put to use in an electron microscopy to get crystallographic information about the images which we obtain in the sample. It's clear? Okay. Then generally to get the magnified image, what we do, because one lens, if we try to use it, there are a lot of problems are there, because if we increase the magnification of the lens, lot of lens aberrations will increase, we can't use it. So what we do is multiple lenses are used of different magnification, so that the required magnification we can reach in a microscope. Then the other one is that on the screen, if you wanted to see the image of the sample, or we wanted to see the diffraction pattern of the sample, what we do essentially is for the further lenses, this lens, if we keep it in such a position that the back focal plane become the object for it, then we will be form an image in the screen, which is going to be diffraction pattern. If the image plane of the objective lens, if that forms the object, okay, by keeping the position of the lens, or in an electron microscope, it's the electromagnetic lens, we change the current which is applied to it, so the focal length is changed, but the lens position remains the same. That's what is done in this case, so that we get the image on the screen. So both the information we can obtain in a microscope. Okay, this clear? And but since we are using electrons, the sample has to be really thin. Okay, so what we essentially get it in a microscope essentially is information from a very thin region of the sample, and that is about the sample thickness should be less than 100 nanometers. Okay. This is so far we talked about diffraction and imaging. So when we image looks at it, we get a contrast, correct? That's a contrast is the one with which we are able to see objects. If the contrast remains the same, if the contrast scattered from all your faces remains the same, I will not be able to distinguish whether you are sitting here or not, correct? I can distinguish it everybody because there is some contrast variation is there. So what is contrast? Is nothing but the rays which are entering some quantity of incident beam is entering into it. Now that beam as it comes out, the amount of beam which is coming in the same direction, okay, that is some particular value. If that remains the same from all the regions, remains the same, then there is no contrast, correct? If there is a variation, like in this sample an amorphous material, this is what is going on. As the thickness changes, the amount of radiation which is absorbed changes. So this is going to make a difference in the contrast. correct? Similarly, if this region contains with a low Z element and this region high Z element, then again there will be a variation in contrast. So this is what with which we are able to find out the microstructural features in a sample. This clear? I am all trying to give only a very qualitative, a crude picture of it, but I think this is very much necessary that you should know this when you do microscopy. But what happens in the case of a crystalline material? In a crystalline material, as the beam passes through the sample, okay, since it's a crystalline material, the diffraction phenomena occurs. Depends upon whether that particular orientation, okay, it is oriented for a Bragg diffraction to take place or not. Depending upon that, the intensity of the radiation which is scattered away from the primary direction is going to change. That means that suppose different grains are going to be there and each grain is oriented in a different way, the scattered intensity will be different of the transmitted beam, similarly of the diffracted beam. So if I try to form an image only with the transmitted beam, this variation intensity which is going to be there at the back of the foil is what we see as a magnified view, which is the image in the TEM. You understand that? Okay. This contrast is called as a diffraction contrast. Okay. Then this is all essentially depend upon this formula 2d sin theta equals n lambda or lambda, you take it. Okay. Suppose a defect is present there. What does the defect do? What is the role of a defect in a otherwise a perfect crystalline material? It it changes the d or changes the atom position. So displacements are going to take place. That means that locally there is going to be a variation in d. So the diffraction effect is going to change from region to region. That is what gives rise to a contrast. That's how we are able to see the defects in a material. You understand that? Okay. That is what I had explained here also. The intensity of the radiation from each region depends upon to what extent that region satisfies Bragg condition. That depends upon the atom position. Okay. At the back of the foil there is a spatial variation and this is responsible for bright field and dark field. So this, no, I just want to ask you, you have used microscopy, any of you are aware of it? Okay. No, that's why I am just going at a pace so that I think one should have a brief idea of what a microscope can do. Okay. So what a bright field and dark field is, if you try to image using only the transmitted beam, then we call it as a bright field. Then the diffracted beam, different diffracted spots will be there. If we use them to form an image separately, we call them as a dark field. But the information is, if all of them we try to take it and combine together, then only the maximum information comes from the material. Okay. Then, and another advantage in a microscope is that we can introduce apertures at some image plane, okay, so that virtually it can choose a small region in the sample, because if you wanted to put an aperture in a small region of 100 Armstrong region, it's difficult to choose. But if you put an aperture which is large one, so this will be acting like an effectively having a virtual aperture like a demagnification, so that will be using this even in a polycrystalline sample, we can choose a small region which is crystalline and get diffraction information and image information from that. And depending upon the size of the aperture we choose it, whether we can have a polycrystalline material or microcrystalline, all these samples could be, depending upon that various types of diffraction pattern will come. Similar to that, in the diffraction also, depending upon the material, okay, we can have using these diffraction spots, we can have images, we can get it using bright field or using dark field, and these images we can obtain. Okay. Yes? Microcrystals is essentially depending upon the size dependence. You can have nanocrystals also. Okay. Polycrystalline material, if they are in the micron or submicron ranges, we call microcrystalline material. Okay. So these are all the information which you can obtain, and this contrast variation which is coming because different regions are oriented differently for diffraction. Okay. This is how a microscope looks like. Okay. This is just for information. There is an gun, electron gun, where that electrons are accelerated to about 200 kV, and then there are some condenser lenses are there. The job of condenser lens is to produce a uniform illumination on the sample surface, because the beam which falls on the sample should be uniform spatially. Then only we can say that the contrast, if the beam itself is fluctuating, that itself will give rise to a variation, then we cannot talk about that image, correct? So that is what the condenser lens does. Then this is where that sample is being introduced, and we have some intermediate lenses are there, 3 projector lens with which it is seen on a fluorescent screen, where that image or diffraction pattern we can get it. Okay. We can go up to magnification of 500,000 to 100,000 magnification modern microscopes. Okay. Another thing which is very important is that suppose you have put a sample. Okay. For any of this information, you have to get diffraction information also to identify dislocations. Quite often, one micrograph you can't get all the information. That I will come to shortly, why it's necessary. You have to tilt the sample to different orientations and image them in a condition which we call it as a 2-beam condition. Suppose we are tilting that sample, okay. This is one pattern which we get it in FCC, and this is another pattern which we get it with this after tilting to 45 degrees. But when we say that we have a crystallographic information, we have to index them. So this pattern I can index them. This is a pattern where the beam direction is along 001. In cubic system, there are 3 001 directions are there, correct? All of them are equivalent, and this corresponds to 110 type. So that 6 are there. But when we rotate a crystal, once we have fixed the coordinate, depending upon which direction which rotate, the directions are now fixed. So when we index the pattern has to be indexed accordingly, correct? If we don't do it, we will not be able to get correct information about the sample. Correct information about the defects which we wanted to analyze, we will not be able to do it. That is very much necessary. That can be done. This is what I had just shown here. This can be done using a stereogram. You have studied about stereographic projections. Okay, stereographic projection is very much necessary for correct indexing of different diffraction patterns which you get it when you consistently tilt from one direction to another direction. Diffraction pattern is nothing but a reciprocal lattice. Okay, reciprocal lattice is what it is. It's a lattice which is created for a crystalline material. Okay, there is an one-to-one correspondence between reciprocal lattice and a diffraction pattern. Okay, but in a reciprocal lattice, what we do is that we consider a lattice. We don't consider atom positions into that consideration. But when we consider real materials and we consider diffraction, we consider the intensity which is corresponding to it. Okay, those are all the things, and the finite size of the sample we will consider, because of which we can have the spot size, streaking, and all those things will depend upon what is the type of material what is the type of sample size which we consider. Okay, but otherwise this is reciprocal lattice. So here in this, what is stereographic projection? Stereographic projection gives all the crystallographic information about the sample, which is essentially like this sample. If you take it, I had just shown a cubic system FCC. Okay, 111 direction will be in this direction, 001 plane is in this one, these are in this particular plane. Different planes are in space in different directions now. But angular relationship you have to express it. If you can, but looking at 3 dimensions is going to be very complicated. If we can express them in 2 dimensions and all the angular relation, that is what is being done in this stereogram. Okay, in fact, in this stereogram, if I look at this 001 which is centered to it, all the spots on this circle are 90 degree away from it. That is nothing but equivalent to when the beam direction is there, all the diffraction spots, the G vectors are 90 degree away from it. So that way we can try to index using these patterns, the diffraction pattern. Accordingly I can index it. This is 100. So corresponding to that in FCC this will be 200. That is how this indexing is done, which you can go through this slide later leisurely and understand this. I am only just telling. Similarly, if I tilt this from here to 0, 1, 1 if I come, okay, then what it will be happening is that when I tilt it in this direction, the similar, this one, the patterns also 0, 1, 1 if I take it, these are all the spots which has to come, then the 1, 0, 0 will remain common. Okay, that is how we have done all these indices, this pattern, these indices, indexing which has been done here and given are corresponding to that. So that we know that the crystallographic directions are fixed even if I tilt that sample. So when we image using different specific reflections, okay, we know which reflection we have used specifically. That information is very much necessary for any analysis in microscopy if you wanted to do a serious microscopy. Especially with dislocation analysis, it's very much necessary. Okay. Then another thing which is important is that when we look at that image is essentially coming because of high energy electrons interacting with that sample. Okay, it's a quantum mechanical effect. So to interpret the images, that I will come to in the later classes, why it's necessary, that they give rise to some contrast. We should know what that contrast means, na? From which type of defect has given rise to that contrast. Okay, this all has been worked out, we know many of them are available, but still it's better to know what it is rather than looking like a blind box. That's why I want to tell. For that, what is important is one is theory which is called as a dynamical theory. What is the essence of this theory? Since the electron beam, since we are using electron beam and electron strongly interacts with matter, as it passes through the sample, the same electron is scattered in one direction from here, Bragg scattering, and then another atom when it comes, it is again scattered. You see that in the same direction the beam is coming. Similarly, from this direction again, so multiple scattering is taking place in the material. Whereas when we do an X-ray diffraction, we assume that when the X-ray beam enters into the sample and comes out of it, it's only a single scattering event. Okay. The theory developed on quantitative imaging using that is called as kinematical. The one which is taken using this is called as dynamical. Here essential difference is that there is a coupling between the transmitted beam and the diffracted beam, because as the beam passes through the sample, part of the transmitted beam is scattered into the diffracted beam, part of the diffracted beam is scattered into a diffracted direction. So both these processes are occurring in the material. Okay. That means that some equations are written which are called coupled equations between the amplitude of transmitted beam and diffracted beam. And another effect which is very important in this is that, because why I am talking about these two is because quite often to find out the exact nature of the dislocations and its magnitude of bias vector, we have to do a simulation of the diffraction, a simulation of the images, for which all these parameters should be known. Okay, that's why I am. So here, if you look at it, as the transmitted beam passes through the sample, the beam passes through the sample in the transmitted direction, you can see that depending upon how they are scattered, the intensity of the beam gradually comes down. There is a distance over which the intensity of the beam can become 0. That distance is called as psi g. Okay, this is a characteristic of the atomic number of the element and the crystal structure. Okay, quite often in all the calculations, you will notice in all the book on electron diffraction books which you see it, even the thickness of the foil is always represented in terms of this psi g. You understand? So this parameter is a very important parameter. So what is the essence of the dynamical theory? So we write some equation where what we are trying to do is, as a function of depth as the beam passes through, how initially the transmitted intensity is maximum, diffracted intensity is 0 on the top of the foil. As it passes through, there is a variation as a function of depth for both of them. That is what is given by these equations, coupled differential equation, and the solution to this gives some expression of this form. Okay. What is the consequence of this? Okay, is that if we take a foil, okay, which is a wedge shaped one, the thickness of the foil varies here as the beam passes through different region, the foil thickness is different. Depending upon that, the intensity on the sample fluctuates. Even if it does not contain any defect, you get a fringe pattern on the sample surface. This is a contrast which you observe, it is an inherent property. This is one which one should remember. Okay. Then the other one is that if the foil is parallel, the thickness remains the same of the sample, and you assume that the sample does not contain any defect in some of the regions, then the contrast has to be uniform. Correct? That is what you see in this sample. This is a sample which is a very annealed nickel based superalloy. You see some dislocations are there which are in planes. Since it is analyzed, I can tell that this is a dislocation. Okay. And then if you look at the this one, the contrast, it appears dark. When it appears dark, what does it mean? What you can conclude from this? This contrast appears dark. Since you have heard the story, you should logically conclude. From those regions, strong scattering has taken place in the transmitted beam. Okay, this is what it happens. So the contrast arises because of this. Okay, but you know that the dislocation, if you look at it, most of the disturbances are around a small region of 3 times Budget's vector or 5 times Budget's vector. So that is the region from which this type of contrast is coming. So essentially, when these sort of contrast variations are there, that is an indication that some defect is present in the material. The region which does not show any contrast, there are no defects, but in the case of dislocations or many defects, there are some conditions under which these defects will not be seen. So one should not assume that the defects are not present. That is why it has to be imaged under various diffraction conditions. Okay. This I will come to shortly. Okay. Okay. Then another important factor which you have to see it is that this factor, if you see, that's Ig into this one, yes, is what we call it as a deviation from the exact Bragg condition. That is, if the planes are there, we consider the sample which are essentially like this. Okay. If we assume that there are some dislocations are there, any type of defect could be there. These regions, if they all satisfy the beam and it falls, satisfy the same Bragg angle, here it's bent, it will be deviated. So this deviation could be represented in terms of a factor S. Even if a defect is not there, we assume that the sample is tilted. Now how much is the tilt? Depending upon that, the intensity of the beam which is scattered will change. That is what this parameter gives. Okay, this is a very important parameter in electron microscopy. In all image simulation, we should have this information. Okay. When we have a defect, okay, what does the defect do? It essentially adds one more term, G dot R, where R is the displacement due to the defect from the exact condition, Ag. This factor also adds to a phase contrast, phase, and this phase is going to bring about change in the contrast. Okay, that's all which happens. So this is the term which is responsible for all the contrast which arises in the microscope. This is what you might have studied as G dot B condition. This G dot R is the defect vector. We will talk about how these defect vectors are related. Okay, this is what I had just mentioned. This statement is very important, that defect changes deviation parameter locally, even on a sample which does not contain any dislocation, like if you can take a whisker which does not contain a dislocation, even in that cases, the sample if you change, contrast will look the same, but the intensity of the image, if you look at it, from one to the other, as you change it uniformly, it is changing. Okay. Another is defect-free region exhibits the same contrast throughout. Both these factors I had explained. Okay, now we will go to the defect. The defects also can be classified into two types of defects. One type of a defect which introduces a strain field around them, and another type of defect is planar defects like stacking faults, antiphase boundaries, domain boundaries, thin precipitates. They essentially produce some displacements. Okay. All these types of defects we will consider it in the course of the series of lectures. Okay. Here what I had shown is a 2D lattice which I had shown. Okay. With respect to origin, when we wanted to find out all the atom positions, we know at regular periodicity. With this vector we can calculate it. So this itself, suppose there is some defect is there, this atom may be displaced from this side. Okay, that is what is given by this vector, and this is the vector which comes into the picture in image contrast. Okay. So these expressions I had already shown, and finally if you try to calculate that intensity, that's how the amplitude changes. It depends upon this function fg, which is essentially a what is that structure factor contrast, the structure factor of the crystal. The structure factor of the crystal is inversely related to that psi g which I had described. Okay. If I write it in terms of psi g, this will be, I will put it as 1 by psi g, I will write it here. And this is integral of this phase, how it changes. This is with respect to perfect region, and this is where the defect is present. As the electron beam passes through the sample, we try to calculate, so we know what is the amplitude at the end, and from that we can calculate what will be the intensity which we will be getting it. Okay. And this for different x and y, because this is the z direction, it is fixed, and x and y direction will be the perpendicular to it. Okay. Perpendicular to a beam. So these are all some expressions which are written. Okay. That same thing which I had already explained, but what is essentially important is, in this expression, if this g dot r defect vector, if it becomes 0, what will happen? Then this expression becomes that for a perfect crystal, correct? That means that depending upon this condition, whether this becomes 0 or whether it is some finite value, we will be able to see the image on the sample, or the image will not be seen. Image of the defect will not be seen. That does not mean the defect is not there, defect is there. That is why we have to image the defect under various g values. This is only for some specific g values, this will become 0. So we have to image for different values of g for which the defect is present. That is how we get a contrast. Then the value for which the defect is absent, that is what is used to find out the defect vector. Okay. And another important is, if this value is less than 1 by 3, okay, generally the contrast is very difficult to observe manually, but nowadays since we use CCD cameras, still we can magnify it and see whether the contrast is there or not. All these expressions were derived when we were using these films to record the images. Okay. Now we will come to dislocations. Okay. Already Fivel has given an excellent idea about how the Burgess vector is defined. Okay. And in this, if you see it, here the planes, if you see, there is a variation in the separation between them, correct? From the normal value. So if the regions which are away from its start diffraction condition, since this region is going to be, the separation is small, you are going to get a contrast which arises from them. The same is true here, because the planes are bent around it, so there is a variation in spacing. So we are going to get a contrast corresponding to it. Okay. Suppose the region which are far away from it, they do not satisfy a diffraction contrast. When the beam comes very close to it, and then the region is bent, from some portion it will satisfy perfect Bragg condition, scattering will be more, and this will give rise to a contrast which we normally observe as the dislocation line contrast. Okay. This will come to show. Okay. But this vector r which we have defined, as I said, is a displacement vector. So if you take a dislocation, okay, the bias vector what we define is what is the vector which is defect vector. But if you look around the screw dislocation, there is a gradual variation of the atomic displacement around the line direction, and that is given by these terms, correct? And this is called as the displacement vector displacement field. Similarly, for edge dislocation also we can have, this is the expression, all these expressions he had also mentioned, okay. Now for contrast from dislocations, that expression which has been derived dynamical theory, we have to use this factor. This is a combined expression for a mixed dislocation, which has both an edge and a screw component. Okay, if the edge component is component is not present, only this portion will come. If the screw component is edge is absent and the screw is there, this is going to come. Essentially, what is being done, how the contrast is or the intensity is calculated, or the amplitude is calculated, is the dislocation is present here. Okay, this is a column. Okay, because we know that the displacement field is long range in a dislocation elastic. So if a dislocation is present here, along this column we are trying to find out how the electron beam is getting scattered. So the effect of this dislocation is region far away from it, there will be atomic positions will be slightly shifted. So this shift is going to affect the intensity which is going to come off the transmitted as well as the diffraction density at this particular point. This we can calculate throughout that sample. That's what essentially which is being done in this case. Okay, this I had done. So the same thing we can do it for a screw dislocation, where that R will turn out to be this one. This is essentially a symmetric around the line direction. Okay. Then in this vector, when we write G dot R, this is B into this is only a factor which is there. So this is the vector crystallographic. So G dot B dot this factor which is going to come into the picture. So nothing but we can write it instead of G dot R, this can be written G dot B into this factor we can write it, because that's a scalar part of it, correct? So if the G dot B becomes 0, then what will be this one? The dislocation contrast will not be seen in the microscope, okay? So that criterion we call it as an invisibility criterion. This is what is used to image dislocation in a sample, okay, or image. Similarly, for a edge dislocation, this is what essentially the R vector which will be. Here again, two terms are there. The G dot R will be equal to G dot B plus G dot B cross U. Okay, both these factors have to be 0. What is G dot B cross U? I will come to it. G dot B becoming 0 is easy, but if the G dot B cross U doesn't become 0, then still some residual contrast could be seen as far as the edge dislocation is concerned. That's what essentially is shown. That is, when an edge dislocation one plane is there, we can see that there is going to be some bulging of these planes from this side and this side. If you see, the planes are perfectly parallel. Here there is going to be the despacing is different. That's what it happens. That gives rise to some residual contrast. Okay. Then another important factor which we have to see with respect to a position of a dislocation in the microscope is essentially, if you see it, this is how the atomic planes are there. This is for an edge dislocation we consider it. So there is going to be a tilting of this plane. When a parallel beam falls onto the sample, okay, the region, assume that away from it doesn't satisfy a Bragg condition. But since this region is bent, some particular point on this dislocation will satisfy exact Bragg condition. So because of that, this beam, the transmitted beam direction, there will be more intensity. The transmitted beam, there will be less intensity. Diffracted beam will be more. So if we image with the transmitted beam, these regions appear bright away from it, other regions appear dark. Not only that, the image which you get it is not corresponding to where the dislocation line is on one side of it. So the image which you see it in a microscope is not the actual image, it's displaced from the ray diagram. If we draw a position where the dislocation should appear, it will be on either side of it. That's what it will happen. Suppose I try to image them with this particular G or with another G, two torque field images. I find that in the images dislocations have disappeared, dislocations have displaced from each other. Okay. Then suppose we wanted to find out the bias vector of the dislocation. What we can do it is, we can image them with different types of G vectors. Okay. We find that for some G vectors, the dislocation has disappeared, but the bias vector of the dislocation remains the same. Correct? So suppose the G vector for which it first disappears is G1, G1 dot B becomes 0, another is G2 dot B becomes 0. If for both of them it becomes 0, if I take the cross product of G1 and G2, I will be able to get the bias vector direction. That is what essentially is done to find out. So what we have to do essentially is image the dislocations with different G vectors, try to find out for which all G vectors it is invisible, and use them to find out the bias vector of the dislocation. Is it clear? This is how the magnitude of the bias vectors can be done. In principle, can be done only for simple systems like disordered systems. If it is ordered systems, even this is not sufficient. That is where we have to do imaging of dislocations. Okay. So how is it carried out? Is in the microscope, you make the beam pass in a particular crystallographic direction, so that you have lots of diffracted spots are there which are equally strong. Then what we do is that we tilt the sample slightly so that only two beams are strong. What essentially we are doing it is that the expression which I had written, the coupled differential equation, is written for transmitted beam and a diffracted beam. The general expression should contain all the diffracted beams. But when we take all the diffracted beam, calculations could be done. Now softwares are available which is done. Earlier when people used to do analytically, it's going to be difficult. So the two beam condition is the one which was used. Even now it's easier to do this calculation. That's what we do. Two beam, what does two beam condition means? The only one particular set of plane is oriented for diffraction. Okay, so that depending upon the type of defect which is being present, okay, from some regions, all the regions there is a scattering which is taking place, but the transmitted beam variation in intensity is due to scattering because of this particular set of planes. So if you try to get that image, this image is coming because of scattering which is taken place in a specific direction. So only these two spots, the central and this spot is considered. This is called as in microscopy parlor as two beam condition. So this is the condition under which we have to image dislocations always. Okay, like this I can tilt it and have different G vectors. Okay, that's what I have done here with respect to these are all the G vectors. With this sort of vector, I can image dislocations. This is what essentially which is being done. Now if you look at these dislocations, here the dislocations are visible, here they are visible. In this condition, if you see that the dislocations are not visible, correct? So doing it like this under different two beam conditions, and if I look at it, here the beam is 001 is the beam direction in the sample. Here it is 001, here 001. That means that the sample has been tilted quite a bit to go from one symmetric orientation to another orientation. Okay, here it is 013. So after doing a lot of tilting, this involves a lot of work. Okay, then afterwards this is only a representative pictures which we do, but many have been taken to do the analysis. From this we can find out what is going to be the magnitude of, because if we know the crystal system as FCC, we know that the close pack distance has to be half 110. From this we can try to find out. How it can be done also is that we know 12 slip systems are there in FCC, correct? Value of G dot B for, we know the bias vector, all of them are going to be half 110 type. Okay, for each one of them, for different type of G vectors, what are the values for which it will give rise to G dot B equals 0, Arjun. This sort of a table we can have. So when we have taken a pictures like this systematically, we can compare with this, and from this basis we can identify, okay, what that exact G vector is, and from which we can find out also what is going to be the bias vector of the dislocation. The same sort of a calculation can be done for partial dislocations also. Okay, we can find out what are the conditions, G vectors and bias vector. This is for an FCC system, because when the stacking fault energy is low, the dislocations always split into partials, right? This sort of calculation which could be done to find out. Okay. Because going into a details and analysis, it will take a one full course to do it. So I am just giving you a flavor and a basic idea, so that when you read books, you can understand what is it to be done. Okay. So far, now what we have understood, I said that to characterize dislocation fully, we require bias vector, line direction, and the slip line. What we have done so far is only the bias vector, how to find out. These are the other two ones which we have to find out. Dislocation. Okay. Here, let us look at a sample, thin foil of a sample, where this is a slip line, okay, in which some 3 dislocations I had just chosen. Okay. And if the electron beam is passing through the sample, what we get in that screen is a 2-dimensional projection of the 3D image. Okay. If this is the line direction, depending upon the beam direction, this is how, because that get a trace, and the dislocation, even though it is there, the projection will be one which is from here to here perpendicular to a beam. That's what it is. So what we get as a direction in this with respect to a diffraction pattern is not the true direction of the dislocation. To get that information, okay, so this is what just I am giving an example how in a reality a dislocation along a slip line when it has moved. This line and this bottom line these are all the 2 parallel lines corresponding to the slip line of the dislocation when this cuts the surface, those 2 directions. Okay. And then these lines are the projection of the dislocation line. This projection direction is not the same as the dislocation line direction. What we require is dislocation line direction, for which SAD pattern is taken from this area. If we take an SAD pattern and we can use a stereographic pattern to determine, okay, and find out this slip line direction and the bias vector, that detail is a total lengthy process which I will not go into it, but I will suggest that one should understand how stereographic projection works. All these things one has to learn. Okay. But what is essentially important here, which one should remember, is that when this slip line cuts this surface of the foil, it creates a line which is direction which is cutting. Na? That direction generally is called as the trace. Okay. But if we consider only this surface of the sample, this line, if we consider it, any plane, even if it is inclined like this, another plane inclined like this, there is one common direction common to it. So from looking at that line direction, we can't get any information about which plane it is lying. All planes which contain that line direction could be there. So that is one drawback. That's why it has to be tilted systematically, and one has to do that. Okay. But when we superimpose the diffraction pattern, we can get some information about what is the direction in which these traces are there. Okay. This I have already informed. That is what essentially I had shown here. This is the trace, and if 2 planes are tilted, the trace remains the same. So from that we can't get that information. So but what we do it is that we have taken, but this is where microscopy comes in the picture. From the same region where we have got the image, we have got the diffraction pattern. Now the diffraction pattern, since it is an electromagnetic lens, some rotation of the image and the diffraction pattern will be there, because electromagnetic lens gives a rotation, because in optical lenses it's only 180 degree. Here it is an angle different from that. All this, when we introduce it, we can superimpose on that and then find out what is the direction in which this trace is lying, what is the direction in which this projection is lying, Okay. These things, if we superimpose on this, that's what this projection which is lying here is lying on a direction which is 0 to 2 bar. So this is this direction, the stereographic direction, and generally this corresponds to, this is the great circle which is corresponding. I don't know whether you have studied all this. No. Okay. Anyway, from this we can try to do an identification. Okay. That part of it I will not go, but you should understand that to get that information about the line direction and the bias vector, first one has to get all the information, analyze it, then a stereographic projection has to be used to get this information. So what essentially has been done is, for the 3 dislocation line directions which are there, these are the line directions which are corresponding. I have projected it on the stereogram, and if I look at this particular direction corresponding to a dislocation 1 which I have marked, which is very close to, this is the great circle, this is 110 pole, which essentially means that that particular direction is very close to 110. That means that the line direction in this particular case is 110 for the dislocation. Similarly, what the line direction is, all could be determined, but for which a serious analysis is required. This itself will take about 1 or 2 lectures to explain how it is to be done. That's why it cannot be done in a short course like this. But I had given a brief idea that it's not just directly you get this information. If you do like this, it's not difficult. You can get all the information about the dislocation. This way, one can fully characterize the dislocation. Okay? And in fact, another important factor also which you have to remember is that this is a sample in which you assume that it's a cube. This is 001 direction the beam is passing through, and this is the foil surface if this is the 001 plane. Okay, this is what it is. Then this is how the 111 plane looks like, correct? 111 plane is cutting this at an angle which is 90, with respect to this one, it makes an angle of 45 degrees. Suppose the same, I prepare a foil in which the sample surface is inclined like this. This is the top and the bottom surface. Then this slip plane, it now cuts on directions. If you see, originally it is in this direction. Now the slip plane cuts in direction. Depending upon the foil surface, how the foil has been done, there are going to be differences. Okay, in the direction which it makes, the trace which it makes on the sample surface. So essentially, what is important is that we should know what is the foil normal to do all this analysis. If a foil is there, you assume it's a single crystal plane in which the area which we are analyzing, what is the plane of that foil? That crystallographic information is very much necessary to do all this quantitative analysis, which it can be obtained in microscope. Okay. Then I had shown some pictures of how dislocations are imaged, but the dislocation has got a finite width. Suppose the dislocation has split into partial, we will not be able to observe all this because it has a finite width. For that, there are different different ways in which these dislocations could be imaged. One is imaging under 2-beam condition, which I showed various images of dislocations. Another is called as a weak beam imaging. That's the one where we can get information about the dislocations, and in some cases when we wanted to find out the bias vector, we have to do simulation of the dislocation also has to be done. The microscopy picture which we get it, when we simulate it, then we can get information about the bias vector. This is just a deformed sample where a lot of dislocations are there. Analysis of this sample, I think one's lifetime will not be sufficient to do for all these dislocations, that I can guarantee you. Okay. This is one which I had shown. Then another aspect which you have to see it is that the same dislocation, if I change the deviation, yes, okay, you can see that how the images look like when s equals 0, s is some positive value but small, and when it is large, the whole contrast will change. When this becomes very large, this image contrast we will not be even able to see. Similarly, the same dislocations which are imaged with different types of G vectors similar to S, you can see that the contrast is varying. See here, this looks like this dislocation cutting for this G vector which I had chosen. Another G vector, you see that it's not cutting. So here you see that another G vector, here it looks like as if they are touching each other, here it does not. It's the same area of the sample. Na? So what do you interpret? If you take only just this picture, we say that there are two dislocations. If you look at this picture, what will you say? So that means that unless you do analysis of these regions, you will not be able to tell correctly about what these configurations of this dislocation, because it's a projected image which you are seeing it. That is where critical analysis of the dislocation. That means that we have to take images under different conditions, then only we can do this analysis. Why I am showing this is because since you are doing discrete dislocation dynamics, and if you wanted to do some microscopy to look at different images, these are all the information which you should be aware of. What is a weak beam imaging? I had just shown you a 2-beam image. There the two central spots are quite closely. If I tilt the sample such that this central spot moves towards this side and this part becomes weak, okay? Or if I take these two spots which are there, this part is weak. If I put an aperture around this part and try to image it, okay, the image which you get, it is called a weak beam image, okay? Or if I tilt this so that this comes, then this is where the one strong spot is there, other strong spot comes very far away, and if I look from here to here, there is way to measure that, and this is called as an evolved sphere. I don't know whether you have studied evolved sphere. So this is the evolved sphere which is cutting it. If the evolved sphere touches the reciprocal lattice, then we say that deviation is 0. When the evolved sphere is far away from it, the deviation is large. This way we can find out the deviation from the Bragg condition. That's what essentially it is being done. Okay. This is exactly what is being done. So essential condition is that when we try to tilt this, since these planes are tilted, okay, if we give more and more tilt, and instead of 3G, 5G we use it, the region from which satisfies the exact Bragg condition, that width becomes narrower and narrower. The image of that will be, that effect of that will be reflected in the image size. Okay. And that is what essentially which you can see here. This is a 2-beam condition strong, and now the same when it is taken under a weak beam condition. Now you can see that a lot of cusps and all, which you don't see it in this image, correct? The images which you can see it, and that image is very sharp. This image is called as weak beam image. Most of us use image dislocations under only weak beam image so that we get the complete information. Okay. And here, this is another one which is taken from the literature. Here you can see that the dislocation has split into partials, and this is the stacking fault which gets imaged, which is imaged under different conditions. All this information you can get it when you image dislocations under weak beam condition. Okay. This is the last one which I will, I think, try to stop it here. I mentioned about simulation of images. You look here, this is a stacking fault which is bounded by partials. Okay. Under some condition, the partial is only visible, the fault is not visible. Okay. If you get an image, what will you think? You think that it's a dislocation which is there, but looking at it you cannot say whether it's a perfect dislocation or a partial dislocation, for which one has to do all the analysis which I had mentioned earlier, characterizing them. The next one which is very important also, this is in a system where the fault of this type could be created by partials with Burgess vectors 1/6 to 1/1, or 1/3 to 1, this twice that of it or 4 times that of it. This is because it's in an ordered lattice. So I do not know which is the partial vector of the, if I use the G dot B equals 0, the condition, the G dot B is also equal to 0, G dot 2B is also equal to 0, 3B will also will be equal to 0. From this condition you can't make out what is B. We can say this is B, but magnitude cannot be obtained. That happens in many cases. Then we have to image them, the dislocation, then do a computer simulation of this image. But to do the computer simulation of the image, we should know G, we should have an idea of, rough idea of bias vector, which what it would be possibly. The line direction should be known, the deviation from the Bragg condition, the thickness of the sample, the foil normal, all of them is an exercise in itself to get it from the microscope. That has to be done. Once all this information has been obtained, then when I do a computer simulation images, this is done using Head and Humble's program, which was about 20 years back, 25 years back it was written. And then now you can see that the image, this particular image, when I take B to be equal to 1 by 6 to 1 bar 1, this matches perfectly with the image which I experimentally obtained, but not these images. Under the same identical conditions, only the B is different. So from this I can conclude that the bias vector of this dislocation partials are this one. This you will face in many situations because you are not going to work on steels. Many ordered faces you will be seeing it. You will see some dislocations within them. Then you have to characterize them. What sort of partials or what sort of perfect dislocations. Quite often this sort of situation also will develop. When that comes, we have to do imaging of dislocations has to be carried out. Okay. With this I will stop here. Okay. Tomorrow I will talk about some, because this is basic characterization of dislocations which I had covered. Okay. Microscopy, about the basics and how we can get this information, what can be done. Then on this basis, then how various types of Frank loops, stacking faults, all those things I will cover in tomorrow's lecture. Okay. If you have any questions, you do please ask. And the books is Carter and Williams' book on electron microscopy that explains most of the things. Now, I will give you in the end of it that the books which are available. Then Jim Hovey, this book, and Fult's book on crystallography, that also gives. Okay. Yes. I will come to that. That's going to be another lecture. That's why I had stopped at this one. Now various types of partials and all in that characterization. Then the dislocation density is one part which is going to be covered. It can be measured. I have done that. There's a way to do that. How to get the dislocation? There are also a lot of pitfalls are there. How to overcome that and do that, I will talk about it. Okay. You have any questions? Or everything is understood very well? Or you did not get a hang of anything? These are only two. Now it's a binary state in which you are there. If you understand, you will ask some questions. Either you understood fully or you did not understand anything at all. Either state, no question comes. Yes? Yeah. Yeah, that is because under different imaging conditions, the partials were visible. You remember here also, partials are visible, the dislocation is absent. That's the condition. So, depending upon the imaging condition, you can get different. That's why I said that what you see in a microscope in one single image, you cannot believe what it is, unless you do a thorough analysis to make out that what you see is the correct information or not. Otherwise, lot of errors we can commit in analysis. Okay. So, I am more trying to tell about what all precautions which you should take. Because one should know the limitation first, then you can do the things correctly. Okay. Yes. Stereographic projection and the evolved sphere is evolved sphere is nothing but to identify a condition under which all reflections will give rise to diffraction. Okay, and that is nothing but another form of writing this formula 2d sin theta equals lambda. If you write it in another form, this sin theta will be, right, 1 by k, and this 1 by d I can put it as d star. Okay, this is the way it is, which can be done. So that sin theta is the Bragg angle. So if you take crystals, okay, that is two-dimensional lattice crystal, atoms are there. Now, with respect to any point in the reciprocal lattice, okay, if we draw a circle with k as this one, okay, then any spot which lies on that, okay, and from here in the beam direction, if I draw, okay, a vector, and that vector is 1 by k, and with respect to this as the center, if I draw, then using this one, all these parts which are lying on it will satisfy Bragg condition, correct? That's what essentially it tells about it. What is stereographic projection essentially is that there are many ways in which we can look at it. Like the way you see me or I see you. What is the way we look at it? We look at this room, it is a perspective projection. All the rays which are coming from different directions, they come to our eye, right? But like for example, I can take with a camera a photograph and give it to you. Will you be able to tell at what positions people are? You know somebody is in front, somebody is in back. But the exact details about it, we cannot do it because this is a perspective projection where one information is missing. Okay, if I know the focal length of the camera and if I tell, then all other information with respect to which you will be able to, otherwise that information is not possible. In a stereogram, what we are essentially trying to do it is that if you take a crystal and put it at the center of a sphere and draw the plane normals from it, and it cuts the center of the circle. Okay, if I take and if I look at that circles which it cut it, okay, from any point on the surface of that sphere, okay, it will be tracing some lines and coming to our eye like a perspective view. And if I take any section cut perpendicular to that, that section is a stereographic projection. That is, I can take it with respect to the simplest way in which I can do it. I have a sphere, okay, from this, I have, these are all the directions in which they are cutting it, okay. If I view it from this particular point, put my eye, and this will be coming like this, this will be coming, this is all coming like this, correct? All this is going to meet at the center on the equatorial plane. These are cutting it. These points, if I try to look at it, from some certain distance it will be coming on this. And from spherical geometry, we know if this is the particular angle it satisfies, what this angle is going to be. In terms of this angle, this radius, it can be distinct. This will, so it will be 2r tan theta, but 2 will come. That means r is the radius of the sphere, that is fixed. So all angles which are there, and if you wanted to know angle between these two ones, it is nothing but the angle between the, on the sphere, what is the distance which it covers, correct? So this angle, half of it, the angle at which this part comes. That means that all the spots which are there in various directions in the sphere has been represented on a plane, maintaining the angular relationship. This projection is called as the stereographic projection, in a nutshell, okay? Is it clear? Any other question? Yes.
You have talked about various kinds of dislocations, like dislocations, like dislocations,
Yeah.
size dislocations, and
Yeah.
sub-boundary and grain boundary dislocations.
Yeah.
How to understand what is the size dislocation?
Yeah.
And how is different from statistical dislocation and then sub-boundaries?
Yeah. What is a sessile dislocation is that when two partial dislocations interact they can form another dislocation which is essentially a sessile dislocation or two perfect dislocations. Okay. This I think I will give it as an exercise to you to solve it, all of you. That is, if you take 1-on-1 plane, it is half 1-1 bar 0, 0-1-1 bar, 1-0-1 bar. These are all the three types of partial dislocation, perfect dislocations which can come in FCC. Okay. What are the types of dislocation reactions which it can happen between them if all of them are activated on a plane they are moving? What sort of interaction which it will be taking place? Okay. You just try to find out. Or another thing which can happen is that if in one plane, that is, I can consider a slip plane like this. One particular plane, there is another plane, that is, in this plane a dislocation is moving, another dislocation, this is moving in this direction, this is moving in this direction. This plane I can give it to be 1-1-1, this plane I can give it to be 1-1 bar 1. Okay. Try to find out what all dislocations, perfect dislocations are possible. If they move like this and try to come, which all dislocations will interact and what it will generate. One of the reaction will give rise to, you have studied Lamar-Cottrell lock? That's a sessile dislocation. Why? Any dislocation whose slip plane is not the closed packed plane, then the stress which is required to move it is very high. In that case, it will turn out to be 0-0-1 zone, a 0-0-1 plane. Okay. So, if we consider an FCC system, okay, I ask you to find out what is the slip plane which it can have. How will you find out what is the slip plane? A cubic system FCC. What do you calculate? Lattice parameters, no? Yeah. You try to find out what is going to be the number density. Okay. So, per unit area, if you calculate, whichever plane has got a number density, that plane will have the minimum frictional stress. Correct? The simplest example is that when you are paving a road and in this carpet is done with respect to some separation, correct? Very fine and closely packed. Suppose instead of it I put a carpet chunk like this, then will you be able to walk fast? Because you find that it's essentially going to be like an obstacle, like a road when you are driving or going on a cycle. On a tar road, you are able to go, correct? Because it's a very smooth one. If instead of that road, I put a lot of stones on it, that's also this one. But where the ups and downs are very high, that is equivalent to how much of energy which you have to take in. So, when the same stone which has been put packed together perfectly, then it requires less energy to go through that. That's what will be. This is exactly what happens. So, when we take this one, find out the planes, assume atoms are having particular ones, separation between size, and then you can find out what is going to be which plane has got the maximum number of atoms which are present. Those planes will have the minimum frictional stress which is required. Those are all the planes which we always consider as the slip planes. In FCC, 1-on-1 is the slip plane. The same consideration when we do in BCC, 110 as well as 112, both of them have got nearly the same packing density, and that is the maximum which you can expect. That is why we call them as the slip plane. Correct? Similarly, the slip direction is the one which has got the shortest translation vector which is there in the lattice. Correct? That is how it is defined. It's clear? Have I answered your question? Yeah, what are sub-boundaries? Cell walls, you know, that is when dislocations interact. Dislocations are generated, they are uniformly distributed in the material at some stage. But still there will be some local variation, dislocations interact, they arrange themselves into a walls region and in between dislocation free region where they move. This happens at low temperatures. At high temperatures what it can happen? These dislocations can climb also, arrange into a network formation. Those are called as sub-boundaries. Sub-boundary is a very general term for it could be a tilt boundary, it could be a twist boundary. There are various things. All these things I will come to and show some examples. Okay. Anything else? So shall we call it a day? Okay. Thank you for patient hearing.